Hello, ladies and gentlemen. We are going to start now. Welcome back to STEM Lockdown Digital School. We're going to continue with physical science where we left off yesterday. We should be on now. I'm having an issue with my screen. Okay, now it's fine. You can get me on Twitter at MosalaDL or Instagram. My handle is post_silicon. Right. Remember that yesterday we were busy with this activity, this exercise here. So let's quickly go through it so that I'll give you a few more minutes just to wrap up what was asked yesterday. So these are the questions. I'll give you exactly 6 more minutes to go through the activity. I'll be giving you 6 more minutes just to wrap up the activity to make sure that even those who are joining us are able to follow what we are doing. So you've got the next 6 minutes to start to go through this exercise. Those of us who are joining us, we just completing yesterday's exercise so that we can wrap it up and continue with today's lesson. Just complete this lesson. I think you are done. Let's go to the next page. Right, those of you who are joining us, we just finishing completing this exercise that we started yesterday. We'll just quickly go through the responses, the answers, and then take it from there.
Mr. Musala,
Yes, ma'am.
there's a few students that wasn't here yesterday.
Okay.
They're all saying that they missed. There's about 4 students that's commented so far that they weren't here yesterday. If you could maybe just give a quick recap on what you did yesterday, not spending too much time on it. Just tell them what they missed.
Okay. No, I will just recap what we did yesterday. Yesterday we did chemical bonding, and then we also define a bond length, bond energy. We also look at covalent bonding. We look at electronegativity. So this exercise will help us also to wrap up the topic that we did yesterday. So let's just quickly go through maybe the responses will then help us to link with what we did yesterday. So the first question here was, let's continue with the responses because we're gonna run out of time. We are asked what is a chemical bond? And then a chemical bond will be a mutual attraction between two atoms resulting in simultaneous attraction between their nuclei and their electrons. So that's a chemical bond. So it's a mutual attraction between two or more atoms resulting in a simultaneous attraction between their nuclei and the electron cloud. And the second question was to draw Lewis structure for HCN. So this is how you draw the Lewis structure for HCN. It will be 2 electrons around the hydrogen atom. And these 2 electrons will also be shared with the carbon atom. And then you'll also have a 2, 4, 6 electron that will be shared with carbon and nitrogen. And remember, there are lone pairs around the nitrogen. So that is the Lewis structure for HCN. And then you can see around the carbon atom, there are 2, 4, 6, 8 electrons. And even around the nitrogen atoms is 2, 4, 6, 8 with this lone pair. So the molecule is stable because it is having maximum number of electrons around each and every atom. Now let's carry on. Let's look at water. Water is having around the oxygen, we've got this 2 electrons that are shared with this hydrogen, and these 2 electrons that are shared with this hydrogen. And then you've got other 2 lone pairs that are not bonded. And then around each of the hydrogen can have a maximum of 2 electrons around it. So each of the hydrogen is having 2 electrons that it has shared, of course, with oxygen. And then we've got 2 lone pairs. Right. Then the next question was, what is the shape of HCN molecule? HCN molecule will be linear. It's a linear molecule. So the shape of HCN is linear. And then you are asked to calculate the electronegativity difference for HCN. So for HCN, you are having the electronegativity for nitrogen will be, for CN bond, sorry. For nitrogen, it will be 3, and for carbon, it will be 2.5. So it will be 3 minus 2.5, which will be 0.5. And then where do you get these values? They will be there on your periodic table. So you should be getting them in the periodic table. It is written there in your periodic table, electronegativity. So you just take a value for each element and then work on it. Right, in this instance, you are having 3 for nitrogen, 2.5 for carbons because it's a CN bond. Right, then the next question was, what is the polarity of HCN? HCN, we are asked to write either polar or non-polar. So in this instance, because nitrogen is more electronegative than hydrogen, so electron cloud will be pulled more towards nitrogen, so the molecule will be polar. And then the next question was to look at this table above. Let me just go back to the table. The table below indicates the values of the bond and bond energy of different bonds in HCN. Now you are having CH, which is having this value and this value for the bond energy, and then CN, which is having 0.116, and then as a bond length in nanometers. And also you are having 890 for bond energy. Now the first question there was that you should explain why the bond energy of CN is more than the bond energy of CH. So the expected response was that CN has high bond order. That is, it is having triple bond, whereas CH is having just single bond. It's a single bond. So it will have a little bit of high bond energy. And then, well, as I've mentioned that CN is just having, CH is having a single bond, and CN is having triple bond, so it will have more. Let's go back to our molecule to look at it. You can see that CH, there are how many bonds? 1, 2, 3, and then for CH is only this shared pair of electrons, so it's a single bond, here it's triple bond. So that is why it is having high bond energy, because it is having high bond order. Right, the other question was, explain the difference between bond length of CH and bond length of CN. So for a similar reason, CN has longer bond length than CH because H atom is smaller than CN. So because of the size of hydrogen atom is smaller than a nitrogen atom, the bond length of CH will be smaller than the bond length of CN. CN will be longer because N nitrogen is a larger atom. Right, the question was, will HCN be soluble in water? The answer should be yes. And then the reason for that, it will be they are both polar. That is, remember, water molecule is polar, and then we have said that HCN is also polar. So likes dissolve like. So that is why it will be soluble in water. So let's carry on with today's lesson. So today's lesson will be based on intermolecular forces. So at the end of this day, you should be able to name and explain different intermolecular forces. That is the van der Waals forces. Hello? All right. And you should be able to describe the difference between intermolecular forces and interatomic forces, that is intramolecular forces, using diagrams of group of small molecules and also describing that in weight. And then you should be able to state the relationship between intermolecular forces and molecular mass. How does the molecular mass affect the intermolecular forces? And then it should be also be in a position to explain the effect of the intermolecular forces on boiling point, melting point, and vapor pressure, as well as solubility of a substance. Right, so let's carry on. Let's deal with the types of the intermolecular forces. We've got mutual induced dipole or London forces. So this is the force that exists between non-polar molecules, like for instance, your methane molecule, your oxygen molecule, and your chlorine molecules. Those that are non-polar, they will have London forces. So the London forces, it is just a mutually induced dipole. So it will be a mutually induced dipole. So you can see here, you can have neutral atoms or neutral molecules, and then at a later stage, you will have polarized atoms or molecules. In that instance, you will have them coming together because one end of the same molecule will be slightly negative and the other one will be slightly positive. And the other end will be of this, another molecule or atom will be slightly negative and the other end will be slightly positive. So the two ends, the end that is slightly negative and of one molecule and the end of the other molecule that is slightly positive will attract each other. So that's how the mutually induced dipole forces work in the London forces, or the London forces rather. Mutually induced dipole forces are also called London forces. And we've got another type of intermolecular forces that is called dipole forces. These are forces between two polar molecules. So the molecules naturally will be polar. So let's look at the other one. It will be dipole-induced dipole forces. This is the case whereby you are having forces between polar and non-polar molecules. So in here, you are having a polar molecule inducing dipole on a non-polar molecule, and the two are attracting each other. For instance, you can have a hydrogen chloride and chlorine molecule inducing dipole on a chlorine molecule, and they will be attracted to each other. And then reason why oxygen is soluble in water is the fact that water can induce dipole on a water molecule. Sorry, water molecule can induce dipole on an oxygen molecule, and the two can be attract each other. So in that way, you will find that oxygen will be dissolving in water. And then let's look at the example of dipole forces. Let's take acetone, which is normally a component that is normally used for, it is the liquid that you normally use to remove nail polish. Yeah, it's a nail polish remover. There's a scientific name will be propanone. So let's look at this molecule here. You are having the two sides, the side with a methyl group and the other side with oxygen group. So this side with oxygen group, because oxygen is more electronegative than a methyl group, so it will draw electrons towards itself, making it this side to be slightly negative and this side to be slightly positive. So the same will happen to this side. It will be slightly positive and this one will be slightly negative. So the two molecules, neighboring molecules, can have forces of attraction, because this slightly negative side will be attracted to the slightly positive side of this molecule, and the same thing will happen. This slightly positive side of the molecule will be attracted to the slightly negative side of the molecule. All right, let's carry on. An example, we have talked about a hydrochloride and also chlorine molecules. So you can see that this is polar naturally. So it will induce polarity on this molecule. And then also we have looked at, let's go back, also at the water molecule and oxygen. So remember, the water molecule is polar on its nature. Now, let's look at hydrogen bond. A hydrogen bond is the forces between molecules in which hydrogen is covalently bonded to nitrogen, oxygen, or fluorine. They call it a special case of dipole moment. So let's look at the water molecule, how it looks like. So this side, because we have said that oxygen is more electronegative than the hydrogen. So the side with of water molecule with oxygen will be slightly negative, and then this one will be slightly positive because oxygen will be withdrawing electron clouds towards itself. The same will be happening to this molecule. So like I've said before, this slightly positive side will be attracted to the slightly negative side of this molecule, and this slightly negative side of this molecule will be attracted to the slightly positive side of the neighboring molecule. Now, hydrogen bonds are stronger than other van der Waals forces. That's what you need to remember. And then the next type of hydrogen bond, sorry, the next type of intermolecular forces is the ion dipole forces. So this is the forces between ions and polar molecule. For instance, you may have a sodium chloride dissolving in water. So this is ion dipole is responsible for dissolution of ionic compounds in polar liquids like water. So in this instance, here it's supposed to be a plus because it's a sodium ion. It will be attracted to the negative side of the water molecule, and the chlorine side, the chlorine, which chloride, not chlorine, which is having a negative there, it will be attracted to the positive side. So that's how it was sodium chloride dissolved in water. Right, let's continue. Remember, we had to distinguish between intramolecular forces and intermolecular forces. So what are the intramolecular forces? Are also called interatomic forces. Intramolecular forces are called, intra means within the molecule. So these are the forces within the molecules, and they are basically bonds. They are interatomic forces. They are forces between the atoms. So these are forces that hold atoms together within a molecule. So as I've said, they are within a molecule. They are intramolecular forces. Now, let's just use this diagram to distinguish between the two. But before that, let's just define intermolecular forces. So intermolecular forces are the forces that exist between the molecule. Intermolecular, between the molecules. So now let's look at this diagram. You can see here the interatomic attraction of intramolecular forces are forces within the molecules. They are interatomic, between the atoms in a molecule. Now, let's look at intermolecular forces. Intermolecular forces, we can see that they exist between the neighboring molecules that are between the molecules. Intermolecular forces or forces of attraction are the forces between the molecules. Now, for nonpolar molecules, the strength of induced dipole forces increase with molecular size. That is, if the size of a molecule is increasing, then the intermolecular forces will increase. Now, boiling point and melting point increase with the increase in the strength of the intermolecular forces. What does that mean? that mean? It simply means that molecules with stronger intermolecular forces will have higher melting points and boiling points. Right, what is a boiling point? A boiling point is a temperature at which vapor pressure of a substance equals to the atmospheric pressure. Right, it is the temperature at which vapor pressure of a substance is equals to atmospheric pressure. And then the stronger the intermolecular forces, the higher the boiling point. So the melting point is also the temperature at which the solid and liquid phases of a substance are at equilibrium. So melting point is the temperature at which the solid and the liquid of a substance are at equilibrium. So remember, there are normally these grammatically correct definition, but these definitions of a boiling point and a melting point are the most scientifically appropriate definitions. So the stronger the intermolecular forces, the higher the melting point, meaning that substance with strong intermolecular forces will have higher melting points. And then vapor pressure is a pressure exerted by a vapor at equilibrium with its liquid in a closed system, right? Let's carry on. So the stronger the intermolecular forces, the lower the vapor pressure. And also, this means that substance with higher boiling points will have lower vapor pressure. Let me give you an example. If we are having petrol and water, because petrol is having lower boiling point, it will have higher vapor pressure than water. So that is what it means. So substance with higher boiling points will have lower vapor pressure. Right. Solubility is the property of solid, liquids, or gaseous substance, which are normally called solid, to dissolve in a solid, liquid, or gaseous substance to form a homogeneous solution. So generally, polar solids dissolve in polar solvents, and non-polar solids dissolve in polar. Non-polar will dissolve in non-polar solvents. So what are we saying? We are simply saying like dissolve like. So polar solutes will dissolve in polar solvents, and non-polar solutes will dissolve in non-polar solvents. Right, let's give you some few more minutes to do this activity so that we can wrap up this exercise. You've got 7 minutes to do this exercise. I'll give you 3 minutes for this 2 and 4 minutes for the other one. So at 11:31, we'll be moving to the next set of activities, and then
Mr.
we'll
Masana?
Hello?
One of the students has posed a question, how do you know what the intermolecular force is?
Okay. In that instance, you look at the molecule. Okay, let's just quickly look at this particular water. Water, it is polar and it is having hydrogen. It is having hydrogen bonded to oxygen. So it falls under the category of those substances that will have a hydrogen bonding. So is ethanol. Ethanol is having oxygen and bonded to hydrogen. So these two will have a hydrogen bonding. But this one, you are having, it's a non-polar because the electrons will be shared evenly between the two bromine atoms because they are having same strength of electronegativity. So it will be a non-polar. So this one will have induced dipole. So it will be this one. Right. So you look at the molecule and also the polarity of the molecules and also the atoms that constitute the molecule. Then you'll decide from there. Okay. I'll try to, if you find time at the end of this lesson, we'll go back to try and explain it further. So we should be able to afford that. Okay, let's move to the next set of questions. Okay, one more minute. All right, your time is up now. Let's start with solutions. The first question was, explain why ethanol is soluble in water. Refer to the strength of the intermolecular forces in ethanol and water. So, like I've explained earlier on, both ethanol and water are polar. So they are polar. So it means, remember we have said that polar solvents will dissolve a polar solids. So hence you are having water dissolving in ethanol dissolving in water. So because they are both polar, and in terms of the intermolecular forces, they are also having hydrogen bonds. The two of them are having hydrogen bonds. Right. The next question was to explain why the boiling point of iodine is higher than that of bromine. So if you look in your periodic table, you'll see that bromine is, they are on the same group, that is group 7 or 17, and then bromine is on top of iodine, meaning that iodine is heavier than bromine. So it is bigger than bromine. So iodine is larger than bromine. It will have stronger intermolecular forces. That is, the induced dipole forces will be stronger than those that are in bromine. So remember, we have said that in terms of non-polar molecules, if we are having molecules with a larger molecular weight will have stronger intermolecular forces. So molecules of iodine, because iodine is heavier than bromine, will have stronger intermolecular forces than bromine. Right. And then the next question was, explain why phosphine will evaporate faster than ammonia. And then you must refer to the types of the intermolecular forces present in each substance. So if you look there, phosphine will have dipole-dipole forces, and then ammonia will have hydrogen bonds, which are stronger than dipole-dipole forces. So that is why, so meaning that the intermolecular forces in phosphine will be weaker than those ones that will be in ammonia. So as a result of that, we have said that substance with weaker intermolecular forces will have lower boiling point. So it means the boiling point of phosphine will be lower than that one of ammonia. Hence, phosphine will evaporate faster. Then where you are asked, water, ethanol, and bromine are liquids at room temperature. Which one has the highest vapor pressure? So the answer should be bromine. Why bromine? Remember that water, if you look at water, water is having stronger intermolecular forces because it is boiling at 100 degrees Celsius. And ammonia, it is boiling at what? Ammonia, which one? Oh, ethanol. Ethanol is boiling at 78. Sorry, it's water which is boiling at 100 degrees Celsius, and then ethanol is boiling at 78. So the two of them are having higher or stronger intermolecular forces because they are having higher boiling points. And then if you compare them with bromine, bromine is boiling at 58.8 degrees Celsius. Its boiling point is lower. So it means it will have higher vapor pressure. Now, we have already given a reason for the answer in 4. So I think that wrap up our lesson. But before we go out, we move out of this lesson, Milani, may you repeat the question again?
Yes, the question, I'm just scrolling up here. How do you know what the intermolecular force is?
Okay, let's go back to our slide again.
Thank you.
Right. How do you know? Remember, we have said the London forces will be the forces between non-polar molecules. So if a molecule is non-polar, you would expect it to have a London forces. So molecules like methane, carbon tetrachloride, oxygen, chlorine molecule will have London forces. And then the dipole-dipole forces will be the forces between two polar molecules. So the polar molecules will be, for instance, your acetone, which is also known as propanone. And acetone is commonly used as a nail polish remover. So that one will have dipole-dipole forces. Dipole forces exist between the forces between the polar molecules. And then the next one, it is dipole-induced force, dipole-induced dipole forces. So this one, it is where you are having a polar molecule and a non-polar. So an example of a polar molecule will be your hydrogen chloride, and the non-polar will be chlorine. So if we are having the polar and a non-polar molecule coming together, the polar molecule will induce dipole on the non-polar molecule, and the two molecules will be attracted to each other. And then they will have forces of interaction. So an example is also between water. Water is polar and oxygen is non-polar. So hence, oxygen is able to dissolve in water because water can induce dipole on water, and oxygen will then dissolve in water. And then we have also said hydrogen bonds. Hydrogen bond exists between between molecules in which hydrogen is covalently bonded to nitrogen. For instance, it can be the hydrogen must be covalently bonded to nitrogen, oxygen, fluorine. So the example of the molecules that are having hydrogen bond will be your ammonia, will also be the water molecule. So here is it there. And then they are stronger, that the hydrogen bonds will be stronger than other van der Waals forces. And the last one, it is the ion dipole forces. So this is the forces between ions and polar molecules. For instance, if you are having sodium chloride dissolving in water, so the positive ion of sodium will be attracted. Sorry, this is supposed to be positive. This positive ion of sodium will be attracted to the slightly negative side of water molecule with oxygen. And where there are hydrogen, the chlorine will be attracted because it is negative. So that's the ion dipole forces. So these ones, they exist between an ion and a polar molecule. Right, I hope I've answered the question. You are following what we are saying. So these slides will be available. They will be uploaded in our website. And remember the definitions that we have used in this session and the types of the intermolecular forces that we have mentioned. And you can also use DBE November question papers just to revise, to check how far are you? And also remember to practice and practice and practice. You can also post questions. Where you don't understand, please don't hesitate to ask questions. And then this is one of the site links that can help you to access more information about the lesson. And further than that, I hope that we have gained something from this session. Let us meet tomorrow, not next week, when we'll be looking at geometrical optics, that is light. You can follow me, you can contact me on mosala.liburu@gmail.com. All it's in small caps, mosala.liburu@gmail.com, or follow me on Twitter, it's @mosaladl, and then Instagram is post_silicon. Thank you for being part of this lesson.
Highlight tomorrow, that would be posted to you guys a bit later. And then just for the guys that's asking for the questions and the answers to be put back, I did add the link for the YouTube channel. You can also just search STEM Lockdown Digital School on YouTube. The classes is available there if you want to just have a look at the class again. Thank you for everybody's participation today. I hope you all have a lovely day further. I am going to end this lesson now.
Thank
Bye-bye.
you, Milani.
Thank you,
Bye.
Mosala. Bye-bye.
Bye-bye, Milani.